we have discussed in last class. So for that, I will share a PDF which I will share after the class, and I will go through the topics that we have covered based on the PDF. I guess all of you can see the screen, the PDF.
Yes, sir.
We were discussing about transient response analysis, and in this regard, we first identified a set of typical test signals and studied the transient response for a first order and second order system with respect to these typical test signals. And then for first order system, we studied the response for unit step response. And for first order, we also studied the steady state behavior of the steady state response. And step response was like this. This is a kind of first order system that we considered 1 by Ts plus 1, which can be recast as a unity feedback system, unity negative feedback system with a forward path transfer function 1 by Ts. And the response we got was something like this, an exponential function Ct 1 minus Ct0 minus T by tau. Now, next, we also found out the unit ramp response. And the response we found was something like this, where this is a unit ramp signal and this is the response. And we found out that for unit ramp response, although the output follows the signal, the input signal, but there is a steady state offset or a steady state error associated with the plant, with the response. Next, we study the unit impulse response. There is like this exponentially decaying function, and ultimately as t tends to infinity, it dies down to zero in absence of any input. Because impulse function is such that it has a non-zero value, it's a unit value at t equal to zero. Other than that, it is having a value zero. And we also discussed about the property that how given a ramp input response, you can find out the step response or impulse response and vice versa. Because there is a correlationship between individual responses in respect of their transient behavior. And we also saw that in terms of steady state behavior, there is no such direct correlation. You have to derive the steady state behavior individually. Next, we consider the second order systems, and it was kind of a response like this, where this was the configuration we considered, and this is the prototype second order or standard form of a second order system. And then we studied the responses for different scenarios like underdamped response, and we derived the necessary equation or the relationship or expression for Ct by these steps, which I have discussed in the last class and which is well documented in this PDF. I'll share this. And this is the form that I've got. Next, for critically damped case, where zeta is equal to 1, we found out the expression for Ct to be this. And for overdamped case, we found our Ct to be this, where the dominant pole, that is the pole which is near the origin in the S plane, has a more prolonged or sustained response. So that will dominate the response, and the pole which is far away on the real axis from the origin, the effect of that pole will settle down much quickly. So the transient response will be dominated by the pole which is near the origin. That is why it is called a dominant pole. And the overdamped response can be approximated by the dominant pole, which is given by this. And these are the different responses that you can see for different case studies. That is overdamped, critically damped, and then underdamped. As damping reduces, the nature of the response becomes more oscillatory. And for exactly damping equal to zero, there is no undamped case. We saw there will be a sustained oscillation with a sinusoidal oscillation with a frequency omega n. This is an undamped natural frequency by definition. Now we are in a position. Let me just copy this figure. Now, given these different scenarios, what we can confer about this or infer about these responses is that there are some typical questions that one may ask regarding the nature of the response, because you have to at first qualitatively state the nature of the response. That be the first impression towards the expression of the nature of the response. Then finally, since we're engineers, we need to quantitatively specify the response. For that, we need some performance indices that to be specified. So what is the problem statement then? Because in many practical situations, the desired performance characteristics are often specified in terms of certain time domain quantities, right? Because most of the systems are energy having energy storing capabilities, and they cannot react instantaneously to any change, so ex- they will exhibit some transient phenomena, and there is certain specification or restriction on the transient phenomena that dictates the problem statement of the control system design. Now, frequently, these performance criteria are specified in terms of the transient response with respect to unit step input that we have already decided. The unit step is the most convenient method of determining the transient behavior of any system. Now, the transient response or the step response of a given system, it may be first order system, it may be second order system, can be easily computed or can be experimentally verified at the laboratory environment. Now, the transient response to the step input, it depends on two very important factors, that is the damping ratio and the undamped natural frequency. So, another important factor is that the initial conditions. Even if we're more prone to the idea that a system will react only when it is given an excitation from an external source. In some situations, it may happen the system will react due to its initial condition. How? Suppose you have a tennis ball that is placed on the table. So it will be at a stable equilibrium point, it will be there as long as you do not force it to move anywhere else. Now, if you put it to a forced equilibrium situation where you have uplifted the ball and put it at a height and keeping the ball on your hand. Now, suddenly, if you release the ball, so actually you are not applying any force due to the potential energy that it has gained by gaining the height with respect to the table. What it will do? It will try to release that energy, it will fall down, and after a subsequent stages of bouncing on the table, just like this, nature of the response will depend upon different qualities of the ball, how much bounce it will be. If it is a say magic ball or a stumper ball, it will have two or three oscillations like this. If it is a solid deuce ball, then it might have a zeta equal to 1, right, to settle down. Or if it is a very heavy, what do you say, the heavy gym balls that you have, where it is full of sands, then it might have a response like this, overdamped response. So, see, this response that it's exhibiting with respect to its position is not due to the external force, but due to initial condition. That is, initial condition means it has a height or a position. That is the initial condition, and based on that, it is giving you a response. The more you lift it above the table, the more potential energy it will gain, the more initial value of energy it will contain, and the response will take much longer time to settle down. Because you understand, each and every time these oscillations are happening, it is basically happening to dissipate the energy so that it comes down to the energy level that is required to be at the table, which is its stable equilibrium point. So the nature of the response will depend on the nature of the ball or the quality of the ball, and based on that, it will have different sets of damping. Right? We have considered the table to be a fixed, say, wooden table. It doesn't have any elastic property. So this is the important thing, that response not only depends on the external exogenous input, but it may also be invoked by some finite non-zero initial condition. Next, now the question then comes that how do we specify quantitatively? So there are two aspects. First is qualitative, And next is quantitative, right? So what are these two things? What are the three basic questions that you need to answer? First qualitatively, then quantitatively. The three basic questions are related to how fast the system moves to follow the input. The next question, how oscillatory it is. And finally, how long does it take to practically reach the final value? So these are the three basic questions that one may ask when specifying a time response. So the first question relates to how fast the system moves to follow the input. As soon as you give an excitation, how fast the system reacts. So we can say it's very fast, it's moderately fast, it's quite slow. This is a qualitative. But at the same time, you need to specify that quantitatively so that you have an idea about whether it is feasible or whether it is apt for the application that you're thinking. Next question is how oscillatory it is. See, for damping ratio more than 1, it is not oscillatory. For damping ratio less than 1, it is oscillatory. And the nature of the oscillation, or the amount of oscillation, depends on the amount of damping. The more damped it is, the less oscillatory it will be. So this is another performance indices that you must specify, the level of oscillation. And that will be specified in terms of peak amplitude and the frequency of oscillation. And finally, the most important thing, that how long does it take to practically reach the final value? Because this is another important aspect. How long does it take to settle down to the final value? Because if a system is too slow to reach the final value, then it may not serve the purpose it is intended to. So there is also this constant is there. So whenever you design a control system, you need to specify these things first qualitatively. Then if they are happy with that, then they'll ask for the quantitative description. So to specify these things, quantitatively, we need some performance indices. And this performance indices characterizes the step response of a given system. Now, what are these performance indices? Let me copy a figure first, because otherwise, if I try to draw it, it take a lot of time. Okay, so this is a typical second order response. Right now, the performance indices that tend to indicate the nature of the response are delay time, then rise time, then peak time, and peak overshoot. These two things. And finally, settling time. See, the first two terms, they correspond to the question with how fast the response is. The next question, next term relates to the oscillatory nature of the response. And finally, the third term gives you the value or the amount of time it takes to reach or to settle down at or around the final value. So these are the time domain performance indices that we need to find out to specify a given second order step response. And these specifications are treated to be universal. Any time response can be specified, will be specified, and shall be specified by these performance indices only. And we'll let us see is this performance indices not only they infer about the time domain behavior, but in some situations they also infer about the relative stability, robust stability, or the frequency domain characteristics. That will come to later. So I'll be redundantly putting this figure over here so that you can understand. First, we have to find out the first thing is the delay time. Now, what is delay time? Delay time is the time required for the response to reach the 50% of the final value. What is the final value? Final value for this system we've already calculated to be 1. So the 50% of the final value will be zero point 0.5. So time it takes to reach zero point 0.5 is your delay time. Next, rise time. What is rise time? It is the time required for the response to rise from 0% to 100% for the first time. Since we are dealing with underdamped case, this is defined from 0% to 100% of final value. That means the time between this and 100% over there. This so this is your rise time. For third is a peak time and peak overshoot. Since we'll discuss about this, the nature of the response is oscillatory due to the underdamped condition. It will reach a peak, and it can be shown that this peak is the maximum peak because it is always encapsulated by an exponential envelope. Okay, I'll discuss about that. So the first peak will be the maximum peak, and you can say maximum or peak overshoot. MP. So this first peak will be the maximum peak, and the corresponding time is called the peak time. And this MP is defined as the amount of overshoot above the steady state. See, the term overshoot means our steady state value is 1, but due to the underdamped nature of the response tends to overshoot the final value and reach a peak. How much it is overshooting the final value is given by MP. And then it again comes down. This is the oscillatory nature of the response. And this MP is defined as percentage overshoot as value of C at TP minus C infinity by C infinity into 100%. So this is a percentage overshoot. I should not say MP, say percentage overshoot. It's better to write as percentage overshoot. Right? And finally, what we have is the settling time. TS. It is the time required for the response to reach and stay within plus minus 2% or plus minus 5% of the final value. See, if this is defined as a tolerance level, although this is your tolerance band, so this response seems to enter the band here, but it doesn't stay within that because it's leaving here. So this is not a settling time. It also enters the band over here, but it is overshooting here or exceeding the band. So this is not also settling time. But when it enters here from this point, then it never leaves the band. So this will correspond to settling time. So it will reach the band and stay within the band. That is the definition of settling time, right? Okay. Now, finally, we can also derive the steady state error. That is for steady state behavior. That I'll keep for later. The other part, it will keep for later. Now, one note about this rise time that I want to mention is that for zeta greater than equal to 1, that is for critically damped, or for overdamped scenario, the definition of rise time is slightly different. What is that? The time range is now, the value range is 10% to 90% of final value. That is the time taken for the response to reach from 10% to 90% of the final value. For underdamped case, it is 0 to 100%, but for overdamped and critically damped case, it is normally 10 to 90%. This is the only difference in the definition. Right? Now, with these definitions, now let us try to find out the quantitative expression for each and every such specifications. But before moving on to that, I shall just give you an idea. আর এদিন ছবি আঁকতে গিয়ে খুব মুশকিল হচ্ছে, ওই জন্য আমি ছবিগুলো আজকে এখান দিয়ে এঁকে দিচ্ছি। আচ্ছা, এটা কোথেকে পাচ্ছি? If we look at the response, this is basically CT for 0 less than zeta less than 1. For another case, this is the expression for CT. Now see, there is a sinusoidal part with the frequency omega d, which is defined as omega n root over 1 minus zeta square. There's also a phase associated with it. And most importantly, with this, there is an exponential term. And this sinusoidal can have a value between plus minus 1, right? When this is plus 1, then what you have? 1 maximum. For this maximum value, 1 plus it is a minus zeta omega t. This minus. So this is one peak of the envelope. this value. And when it is negative, then it becomes this is another peak of the envelope. And for each subsequent value of the sinusoidal signal, this envelope will be like this. So it has a nature, right? And it has a nature like this. This is for t equal to 0, and this is for subsequent values of t. It will be a exponential nature like this, and this exponential envelope defines the amplitude of the output response, or in other words, the output response of this CT will be within this exponential envelope, right? Now, as the damping increases, the envelope will become more and more tight. As the damping reduces, that is, it will be more and more tight as the damping increases. On the other hand, as the damping reduces, it will be more and more flat like this. And typically for damping z equal to 0, you put z equal to 0 over here. So it will be 1 plus 1, 2, and it will be 1 minus 1, 0. So this is for zeta equal to 0, right? So this is how the damping actually will determine the nature or the rate of decay of this exponential functions, right? Now, I have a little query. Since we have seen, just to break the monotonous class, we have seen there are different types of responses like underdamped, overdamped, critically damped. You ponder over the question. You can answer me after a while. I'll ask it again. The question from my side is that, in your opinion, which response, underdamped, overdamped, or critically damped, will be the fastest to reach the steady state, or will be the quickest to reach the steady state? You do not have to answer that right now. Just think about it. Right? Obviously, you will say that overdamped response is the slowest. I agree. So this comes out of the equation. So the next two is critically damped and underdamped. Right? So just ponder the which one will be the fastest to reach the steady state. There are plenty of responses given over here. So I'll come to it later, right? This is one question that I'll ask. I seek the answer later. So this is how the envelope determines the nature of the oscillation or the peak of the oscillations. And obviously, following that, it is understood that the first peak corresponding to this envelope will be the peak overshoot. The subsequent peak will be of reduced magnitude for an underdamped response. Whereas for undamped response for zeta equal to 0, all the peaks will have consistently same magnitude between 0 to 2 for unit step in. Okay, now coming back to the performance indices that we have already specified. Now we should be able to find out each and every performance index. So let's start with rise time, TR. Now the definition of rise time is that at C at equal to TR is equal to 1. It's 100% of the steady state value. So we can write down C of TR is basically 1 when TR cos omega d TR plus. I'm just taking one step back where it was written like this. This is another expression for this. And that should be equal to 1 by definition. This is the CT expression that we have derived in the last class, cos omega dt, zeta by 1 minus zeta square root over sin omega dt. Now from that, what you can write, this one is cancelled out. So e to the power minus zeta omega and tr cos omega d tr plus zeta root 0. Since this exponential function can never be 0, so we can have or we can write tan of omega d tr is equal to root over minus plus what is zeta with a minus n. From that, we can infer that tr is equal to, minus is there, so pi minus tan inverse zeta divided by omega d, right? And this tan inverse 1 minus zeta square root over root by zeta is nothing but, if you remember, these are the two complex conjugate poles that you have. Then if you draw a phasor from the origin, it will have a length omega n, and the angle that it makes the real axis will be beta. That is tan inverse root over minus zeta square by zeta, right? Because this part is omega d and this part is zeta omega n. So if you take tan of beta, you'll get this. So this you can finally write down as tr is equal to pi minus beta by omega d. So this is how we can calculate the rise time for any given zeta value. And omega d is calculated as omega n into root over 1 minus zeta square. Okay. Next, peak time Tp. Now from the definition of peak time, we can write that dct of dt at t equal to Tp should be equal to 0. So if you now calculate this ddt of ct and equate that at t equal to Tp, then I'll just write down directly. What you get is zeta omega n e to the power minus zeta omega n t. The one will be getting cancelled out into this thing cos omega dt plus zeta root over 1 minus zeta square omega dt. This is for the first part, and for the second part, we'll have plus e to the power minus zeta omega n t omega dt sine omega dt minus zeta omega d cos omega dt after suitable manipulation at, sorry, everything calculated at t equal to Tp, that is equal to 0. So if you now put t equal to Tp, and after um, certain manipulation and equating this to be equal to exactly equal to 0, then you'll find out এটা একটুখানি ম্যানিপুলেশন করতে হবে। করার পর তোমরা যেটা পাবে বাই পুটিং টিপি ইকুয়াল টু 0, ইউ ফাইন্ড আউট দ্যাট টিপি omega n root over zeta square এটুকু আসবে। That will lead to this, and that finally implies এটা করলে derivation করলে তুমি এরকম একটা expression, you get expressions like this. So this obviously indicates that this is true for omega d tp is equal to 0, pi, 2 pi, 3 pi, and so on. So you can write down tp as n pi by omega d, any n pi by omega d, but this n, different values of n will correspond to different overshoot. Say for n equal to 0 there will be no overshoot because that is the starting point. For n equal to 1, what is that? tp is equal to pi by omega d, first overshoot, right? For n equal to 2 is 2 pi by omega d, and this is first undershoot. Then n equal to 3 will correspond to tp equal to 3 pi by omega d, second overshoot. Similarly, n equal to 4 correspond to 4 pi by omega d, second undershoot, and so on. So at an interval of pi by omega d, it will reach a maxima or minima, overshoot or undershoot, overshoot or undershoot. So this will continue to oscillate with this damped natural frequency, which is given as omega d. And corresponding to this, you can easily confer that this will be the peak overshoot given by the envelope that we're talking about. Then we will be in position to find out the expression of peak overshoot. That is, which overshoot will be the peak, the highest. So from that, we'll define this peak overshoot as MP. There is the amount of overshoot above the steady state value. So we know the steady state value is 1 over here. So we can calculate MP as C of TP minus 1. So it will come out to be e to the power. So that will be e to the power minus beta omega n. And so the first overshoot means pi by omega d. Then cos omega d, pi by omega d plus zeta root over 1 minus zeta square sine omega d, pi by omega d. So this will be e to the power minus zeta omega n pi omega n, right? 1 minus zeta square because omega d is defined as this. Then cos pi sin pi. Acha, c to the minus 1, there is a minus sign, I missed out that. because 1 minus this and 1 will cancel out. This is there is a minus sign over here. So this will be minus 1. So it will be right. So this will be the expression for peak overshoot, which is directly a function of the damping ratio. Now, if we just try to find out the final expression, that is for settling time. Yes. Now, for an underdamped response, we have already found out that our expression for CT is of the order 1 minus. Eta. So, we already seen that the response will oscillate between a pair of envelope curves given by this, and the envelope, the curve are given by 1 plus minus zeta omega n t root over 1 minus zeta square. And the time constant for these envelopes will correspond to the factor associated with the exponential time. So this is the time constant. Yes, how fast or how slow the envelope will decay down. So for a given omega n, the settling time will be a function of zeta for the same omega n, and for a range of zeta which varies between 0 and 1, the settling time will change correspondingly. Now comes the question. So I've asked you the question that given a response, given a system, the say is equal to 1, in your opinion, whether critically damped response will be the fastest or sorry, underdamped response will be the quickest. Any idea কোনটা তোমাদের কুইকেস্ট হবে, ক্রিটিক্যালি ড্যাম্প না আন্ডার ড্যাম্প, কোনটা আগে সেটেল করবে? বলো কি মনে হয়?
স্যার যেটা টাইম কনস্ট্যান্টটা কম সেটা আগে সেটেল ডাউন করা উচিত।
সেটা বুঝতে পারলাম, টাইম কনস্ট্যান্ট কম, তার মানে
তাহলে এখানে
যেটা
জিটার
বড় হবে তত
হ্যাঁ
ভালো।
মানে তত
তো যেটা
হ্যাঁ
1 হলে তো তার তো তোমার অনুযায়ী তো যেটা 2 হলে তাতে সেটেল করা উচিত। প্রথমত সেটা হবে না, কারণ this this formulation is only valid for underdamped response and this is invalid for critically damped. যদি critically damped হয় তাহলে তোমার যেটাতে কি হয়ে যাবে বলো, এটা এনভেলপটা কি হয়ে যাবে 1/0 ইনফিনিটি, তাই তো কোনো এনভেলপই তুমি পাবে না critically damped এর জন্য। সো দিস ইজ নট ভ্যালিড, দিস ইজ অনলি ভ্যালিড ফর 0 to 1। ফাইন। আচ্ছা হ্যাঁ, এবার যেটা নোশনটা এটা হবে, whenever I ask that whichever response will be the fastest to reach the steady state, the counter question that should come whether any overshoot is allowable or not. Why? See, in many situations where a precision work has to be done, and there is some very delicate instrument that operates, there is a certain restriction. See, suppose there is a manufacturing plant where a robotic arm is putting a very small chip, microchip on a motherboard, right? So the objective is, since this chip has a very delicate legs or pins that needs to be installed at the proper position, so your robotic arm should be so designed that it reaches. So this is a position, initial position. This is the final position of the robotic arm. So it moves like this. So the response should be that it should reach the desired position at the quickest, right? But the other restriction is that it should never overshoot. It should never overshoot the position, because if it tries to overshoot the position, what will happen? It will be exerting some additional force on the delicate legs of the pins, and that might get damaged. So it has to be precise and should not overshoot the final value. This is one restriction. So in that case, you invariably will go for a critically damped scenario. That will be the fastest. Agreed? On the contrary, it is seen that if in any situation where you can allow certain undershoot and overshoot, especially in indicating instruments, if you look at the indicating instruments where there's a needle that first oscillates and then settles down to the final value following any deflection, it is always desired that the needle or the pointer should reach the steady state at the earliest. Now, it can be seen, although it is contrary to the common belief or the common idea that you normally develop in your head or in your concept, that critically damped will be fastest. No, it can be shown that a properly damped, underdamped system will reach the steady state value faster or earlier than a critically damped system. So there are properly damped, there is set of properly damped, and normally it is seen that there is a range between zero point 0.4 and zero point 0.7, precisely in zero point 0.5 to zero point 0.7. If that is the value of zeta, then the time response or the settling time in those situations is better or less than the scenario where it is critically damped. ঠিক আছে, এটা কিন্তু একটু দেখে মনে হয় না, দেখে মনে অসিলেট করছে, যে অবভিয়াসলি সময় বেশি লাগবে, নট নেসেসারিলি। যদি এরকম রেসপন্স আসে, দেখো এই রেসপন্সটা তুমি খেয়াল করো, there is a very less oscillation and it almost settles down at the same rate as that of that. And if you have properly designed a system in between this, দেখো একটা 0.8 আছে, 0.6 থেকে 0.8 এর মধ্যে থাকলে in some situations it reaches down, in most of the cases it reaches down the steady state even before the critically damped system. But there is only one catch. This type of response may not be permissible at all situations. Especially এখানে বললাম যে robotic arm is used for fabrication of very fine or delicate chip. Then you cannot allow such overshoot, because it will damage the legs of the pins, or যদি ধরো কোনো etching করছে, কোনো it's very fine job that you're doing with a very delicate instrument. You cannot force or cannot exert extreme force or additional force so that the tip or the fine part will get damaged. So under that condition, it is always desired not to have zeta less than 1. এখানে ছোট্ট জিনিস বলে রাখি, in robotic arm or robotics, first thing is that you cannot have this underdamped response. So it should be critically damped or overdamped. An ideal situation is critically damped, but since in practicality every system is susceptible to parameter variation, and suppose you have designed the system to be critically damped, and there's a slight variation in the parameter that led to a situation where the system has become slightly underdamped, say 0.95. So there will be overshoot. That overshoot may damage the instrument. That is why in those situations we compromise. We set a value of damping at 1.1 or 1.2, so that Even under the uncertainty or parameter variation, there is a factor of zero point 0.1 and zero point 0.2 of damping. After that, it will become underdamped. So even under the uncertainties or the parameter variation, it will still remain at least critically damped. There's a factor of safety remaining there. Okay, so that's a very typical situation. Normally, that is how we deal with the control problems because it cannot be absolute about such parameters. There are many reasons. First of all, the model that you're using is a simplified, in some situations, oversimplified linear time invariant model. Most of the systems that we employ or encounter in nature are nonlinear. They are time varying. They're susceptible to parameter variation. They're susceptible to modeling uncertainty. They're susceptible to ignorance from our side because we are ignoring the higher order terms. We are approximating the plant to be a second order, but it may contain third, fourth, fifth order. They may even contain zero. We have not considered zero. See, we have considered the system to have only two poles and no zeros. So the effect of zero, we should study. What is the effect of zero? So under this level of complexity, you cannot just fully ensure this is the absolute value of zeta. What you can do, you can ensure there is a range of value that it can take. There's a part of a control theory that deals with certain these things of uncertainty and all. There's a robust control. Okay, there's a separate part and stream of control theory where we design or try to design a control system which is such that it can ensure stability and an amount of performance even under these uncertainties, all the different conditions that I've stated, like nonlinearity, uncertainty, yeah, negligence of higher order terms, interactions, time varying nature, parameter variations, all these things. Now coming back to the expression for the settling time. So we can have two such scenarios where there is a settling band of plus minus 2%. So in that case, you can say that sorry, this envelope, the amplitude of envelope should reach the value 0.02, or we can approximate this as so this will lead to definition of settling time approximately as 4 by zeta omega. This is approximate. Similarly, for a band of plus minus 5%, where you can allow the response to stay within plus minus 5% of the steady state, the settling times following the same principle, sorry, 3 by zeta omega. It is a bit less than this because it reaches the 5% band earlier than the 2% band. Right? Now, what inference that you can draw from here is that R 3 by zeta omega. So it is inversely proportional to zeta omega. Now, this zeta and omega n, can you choose this zeta and omega n arbitrarily to make Ts as small as possible? With a very high value of zeta, very high value of omega n, so that it is always a very less settling time? No, cannot do that because we have already decided or we have already found out that the peak overshoot is defined by this. So once you specify the maximum amount of percentage overshoot that is allowable, that gives a fixed value of zeta. So zeta gets fixed, right? So only unknown parameter will be omega n. Again, this TP, the peak time, this zeta is fixed, and if you also specify the peak time, then omega n is getting fixed. So, on the contrary, if you just specify your percentage overshoot and settling time, then it is proportional to 1 by zeta omega n. So, zeta is already fixed by MP, and this omega n you can choose to match the value of Ts. That's the only free parameters if you have. And if you also specify TP, peak time, then you obviously cannot have any control over TS. So there is always this compromise. Either you compromise on peak time or you compromise on the settling time. So you can say primarily the settling time will be governed by omega n, right? So what should be the value of omega n to get a less peak time, since zeta is constant for MP. If you increase the value of omega n, that means Ts will be less. So you should choose the value of omega n as large as possible. And regarding this MP, if you remember, if you draw this curve, say this is your percentage overshoot and this is your damping. Right? So for zero damping, what is the percentage overshoot? It is 100. And for damping of 1, it is 0. And the nature of this response is something like this. Right? This is the percentage overshoot versus zeta. That is why whenever you specify this percentage overshoot, the zeta gets fixed. You cannot change the value of zeta. Okay. So these are the different scenarios or different performance indices that we may encounter in Verity, and we shall specify our time response in respect of this performance indices related to a standard second order prototype system. Now let us try to put all these things into perspective. Okay, before that, this one thing is left. So far, we have considered our transfer function to be there's a standard second order transfer function. So there's no zero associated with it. What happens if we add a zero? Then what will happen to the response? Now this 1 by z factor is used to make sure that the steady state value remains at 1. So from that you can write down your CS by Rs as omega n square s plus z. I'll just factorize it simply. So 1 will be omega n square by following this z by z s square 2 zeta omega n s omega n square plus this s by z factor. So 1 by z s omega n square s square. See, these two are the same, right? So there's only thing is that this s multiplied by this. So if we write down this, that cs is equal to C0s Rs plus 1 by Z into S C0s Rs. Then what you can write? See, your Ct will be, this is same as C0t, that is the corresponding to the response we had for this system, plus 1 by Z S into C0t. That means this is the differentiation of that, where C0t response of the original system. So how will this actually affect the transient response? Let us see that. Okay. And this is a final steady state value of 1, suppose, and we have our initial response. So this is your C0t. And now what you have as Ct is equal to C0t plus 1 by Z. Now why don't you calculate what should be the value of ddt for 1 by Z? What should be the value? See, to start with, we have assumed that the system is initially relaxed. So C0, C dot 0 equal to 0. So it will start from here, and then it will motorically increases, then decreases, and becomes increases first, then decreases, and becomes 0 over here. Sorry. Increases and something like this. So these points are all related to 0. So if the finally, if we add these two, then the response that you will be getting will be something like this. So what will happen? There will be a pronounced peak, and that will happen even before the peak of the original system due to the addition of this term, and this peak amplitude will be a function of this 1 by Z, and as the 0 moves closer to the origin, the Z will be reduced and the peak amplitude will obviously be increasing, and at this point, since this part is 0, so it will be passing through this at these points. So note, smaller the value of Z, the closer the zero is to the origin, the more pronounced will be the peak. So it will be more and more peaky as the zero moves closer to the origin. So obviously, so far we have not considered the effect of such zeros in a system. But as soon as you consider a zero to be present in the system, the nature of the response will be completely different. And under this scenario, we simply cannot use the formula of peak response or peak overshoot or peak and time rise time in certain time, because now the system equation have changed to these values. This is the overall system. Now the same thing, what will happen if we addition following the addition of a whole. So under that condition, your CS by RS TP is the time constant of the pole. So how the response will be vary? Since this is a third order system, it's very difficult to interpret that, but I'll just try to give an idea just for the sake of information. City. So for TP equal to 0, so this is the typical response for TP equal to 0. That is a second order, actual second order system. Or I should not say second order, original system. Original system. Now for TP equal to 1 or TP equal to zero point 0.5, say TP equal to zero point 0.5, what will have? Now TP equal to 1 and say TP equal to 3. See what is actually happening as TP is increasing, damping is increasing. And I should not say damping, effective damping is increasing. So system has become more and more like over damped, right? This is completely in contradiction to the case in case of a zero, where as Z is reducing implies effective damping is basically reducing because the damping is constantly increasing. Here also TP increasing means your pole location pole tends to origin, and Z decreases mean as zero tends to origin. So there is obviously a contradiction that is expected between the responses of these two scenarios. These are the typical cases, and we'll encounter such problems while designing compensators or controllers. Now, I'll conclude today's lecture by just giving an example. I'll take just 5 minutes more. And going with the same notion that you have been following, our example will be first a RLC series circuit, and that is not confined to RLC series circuit. It may be even mass spring damper or any analogous second order system. This is your input voltage. This is your output voltage. Obviously, these elements are R, L, and C. And we've already found out that this GS, that is your V0S by VNS, is 1 by LC S square. Yes, plus omega square. Oh, sorry. And that should be modeled as, so which leads to the following condition, that omega n square is equal to 1 by LC, and 2 zeta omega n is equal to R by L, that is zeta comes out to be R by 2 root over C by L. So these are two important factors in terms of L and C. And out of the poles, poles are located at minus R by 2. That you should calculate all these things. Square minus 1 by S. Right? Now let us check for different conditions. One, under damped. So this is the scenario when the response will be in underdamped nature. The condition for that is the zeta should be less than equal to 1, or you can write down for R by 2L less than equal to 1 by root over LC. This is the condition. When it follows the condition, then the roots will be at minus J square. So this is the underdamped scenario. Then for critically damped, zeta equal to 1. So that leads to R by 2L is equal to 1 by root over LC, and roots S1 is 2 at minus R by 12 minus R by 12, right? And finally, forward that The condition will be just following the rules and the roots. Right? Right? Now, this is the different scenarios or different conditions. And see, in this each and every condition, if you consider the C to be constant, then by changing R or C and L are constant, by changing the value of resistance, you can have different scenarios. Right? Each and every scenario can be established by varying the value of the resistance R. Now your task will be to find out each and every expression for each and every type of response. That is, find CT for each case. Let's find the expression for CT for each case. That will be a good practice for you to follow. So with this, I'll conclude my lecture for today over here. So if you have any queries regarding today's lecture, you can ask.
স্যার
বলো।
স্যার বলছিলাম ওই ক্লাস টেস্টের ব্যাপারে একটু বলার ছিল
হ্যাঁ,
স্যার।
তোমরা বলো। তোমাদের উপর পুরো ছেড়ে দিয়েছি। কবে দেবে, কি দেবে?
স্যার এই ক্লাস টেস্টটা স্যার নেক্সট স্যাটারডে সেম ক্লাস টাইমে দিলে কি মানে প্রবলেম হবে স্যার যদি কোনো দেওয়া যায়?
ক্লাস টাইমে দিলে ক্লাসটা কখন হবে গো?
স্যার অ্যাকচুয়ালি তাহলে অন্য মানে সবার একটু অ্যাডজাস্ট করতে প্রবলেম হয় মানে যদি অন্য টাইম হয় তাহলে মানে করা যাবে না তা নয় বাট ওইটা ওই দিনটা
তা
হলে ঠিক আছে।
শনিবারই করো, শনিবারে দুপুরে করো।
দুপুরে
স্যার
শনিবারে
ক্লাসের পরে।
ক্লাসের পর say
আচ্ছা
2:30 to 4:30।
2:30 to 4:30 হ্যাঁ সেটা করা যেতে পারে।
আমি ক্লাসটা মিস করতে চাইছি না, এখন বেশ কিছু